Let's switch gears and check out another cool facility here at White Sands that is helping us make our astronaut crews even safer. Come on, let's roll. Now, since the late 1950s, when we started sending rockets and satellites into space, the area known as low Earth orbit has become pretty cluttered. There are millions of man-made objects and naturally occurring micrometeoroids that are swirling high right above our heads. One of the main challenges NASA faces is to be sure structures, vehicles, and spacesuits are safe. But how do you test them to withstand the impact from these small particles? Well, check this out. There's this really cool facility here at White Sands that does just that. Let's head inside and meet my friend Karen Rodriguez, who will show us how NASA tests hypervelocity impacts. Karen, hey, how are you?
Hey, good, how are you doing?
Good to see you. Wow, this place is something else. Tell me, what's going on here?
Well, what we've got here is our remote hypervelocity test laboratory.
Okay.
And what we do is we utilize two-stage light gas gun to simulate micrometeoroid and orbital debris.
So why do you do hypervelocity testing?
Well, there's over 100,000 metric tons of debris in space. And this debris is traveling in various orbits around the Earth.
Okay.
And so we have, of course, the International Space Station in space, and we have the astronauts going up in the shuttle. And so we want to protect the astronauts, the International Space Station, from this debris. This is NASA's #1 risk, and we want to make sure that the astronauts are safe and that they can come home safely to their families.
Of course. So how do you decide what to test?
Well, it's a real interesting question.
Yeah.
Actually, what we do is we work very closely with Johnson Space Center and a group over there called the Hypervelocity Impact Technology Facility. What they'll do is they'll perform an assessment of the shuttle after it has gone into orbit. And when it comes back, they'll look at the size of the debris for the impacts that were created. They'll take that information and look at their existing models and then determine what size of projectiles we need to shoot. Now, we shoot spherical projectiles, but not all debris in space is spherical. But for modeling reasons, it's actually easiest to model spherical projectiles. Now, what they'll do is they'll look at different densities of the materials that are actually in space. So not just micrometeoroids, but of various explosions, impacts, anything that may have occurred in the past that has generated new debris. They'll look at what type of material that is and then choose another material of similar density and choose that material for an impact.
Do you have any examples around here?
Actually,
You do?
we do.
Hey.
Thank you.
What do you got?
So what we've got is a nylon projectile and an aluminum projectile. Now these are just two different sizes, but there's actually a variety of materials that we can test.
Okay.
Aluminum, stainless, glass, anything. So pretty much any projectile that is an inch and smaller we can test. So what we have in here is 50 micron projectiles. Now you can kind of see the dust down there in the bottom, but it's really tiny.
Right.
And we can shoot one of these as a single projectile all by itself.
So here's my question. I mean, why would you want to test something that small? I mean, how can that hurt somebody in space?
Well, the reason we want to test projectiles these small is because there's a lot more of smaller projectiles in space.
But how can that hurt an astronaut?
Well, you've got a more abundant amount of these small projectiles. And because you can't track it, if it impacts the astronaut spacesuit or even a shuttle glass window, the damage varies, and so that's why we do a variety of testing. There's a paint fleck that once impacted the window on the shuttle and it created some damage to it, and then the question being, of course, you've got a vacuum in space, and how does that compromise the material properties of that piece of glass once it's been impacted?
Oh, wow. So Karen, it's really hard for me to understand these speeds, and can you give me an example?
Well, if you can imagine traveling from the East Coast to the West Coast in approximately 10 minutes.
Yep.
That's how fast debris is traveling up there. So it's not just the astronauts that we're wanting to keep safe. You've got your satellites up there that are for your television and for your cell phones, and so who knows what'll happen if those satellites are impacted.
Wow. So this is an actual gun then, right?
Yes.
Yeah, tell us how it works.
All right, this is our 17 caliber launch range.
Right?
We've got our end cap, and this is where the gunpowder is loaded.
Sure.
Now inside here we have a piston. an example of what one of the pistons look like.
Okay.
Now the piston is inserted into the pump tube section of the gun.
Gotcha.
We have a vacuum, and then we fill it with hydrogen. Gunpowder burns, accelerates that piston forward, compressing the hydrogen gas. This is our high pressure coupling. Now what we have in here is a tapered section.
So the projectile is here, right? And the gunpowder is all the way down there, right?
Right.
Why?
Okay. This is a two-stage light gas gun.
Okay.
If you have a single-stage gun,
Right.
conventional methods won't allow you to get to the velocities that you need to achieve to simulate hypervelocity debris.
Okay.
So we have this section of the gun because we need the two stages in order to compress the gas, in order to accelerate the projectile to a high enough velocity to simulate that micrometeoroid and orbital debris. So the pump tube has compressed that hydrogen gas into this section. We have a pedal valve, which then ruptures and allows the high pressure gas to accelerate the launch package forward. So this is our barrel,
Right.
and it has a .17 ID diameter bore, thus a 17 caliber gun. Inside here we have the launch package. The launch package is then accelerated forward from that compressed hydrogen gas
Right.
into our flight range. Once the launch package gets into this section, the projectile then enters free flight. And so we capture the velocity as the projectile breaks the beams of the laser station. The projectile continues down into the target chamber where we have our test article fixed.
Right.
And then we get a nice impact. We collect the images, and when the test is done,
Yeah.
we pull it out, got a beautiful target.
Let's go take a look.
All right?
Come on.
All right, so what's going on now is Paul's opening up the target chamber.
Right.
The test is just finished, and
Sure.
he's getting ready to pull the test article out.
Okay.
Now, see how he took that out right through the crosshairs?
Yeah.
Isn't that great?
Totally. Dead center.
So this is the test fixture
Gotcha.
that they use to mount the test article.
Uh-huh.
And if you look down inside the tank, you can see the barrel is coming through. We've got our flight range,
Right.
and it's coming through, and that's the direction the projectile travels, and it would come through and impact the test article. We have our high-speed imaging systems, which are capable of 200 million frames per second.
Wow.
So what happens is we have the cameras right over here. They shoot across the target chamber, and they capture the projectile in flight prior to impact.
Karen, thank you so much for having us.
All right, Johnny, thank you for coming out. I'm glad to have NASA 360 joining us out at White Sands Test Facility, and hope to see you soon.
You definitely will. Thanks.